Welcome to this video on Kirchhoff's laws and the frequency domain. This is part of a series of videos on circuit analysis in the frequency domain. Let's start with Kirchhoff's voltage law in the frequency domain. Assume V1, V2, all the way to Vn represent voltages around a closed path. Also assume the circuit is operating in a sinusoidal steady state. We apply Kirchhoff's voltage law in the time domain. Then, each voltage is represented using the real part operation. E to the j omega t is the common factor, so it is factored out. Because e to the j omega t cannot be zero, we can write that the sum of corresponding voltage phasors is zero. This is in fact Kirchhoff's voltage law for phasor voltages. Kirchhoff's current law for phasor currents can also be obtained in a similar manner. According to Kirchhoff's current law for phasor currents, the sum of current phasors at a node in a circuit operating in a sinusoidal steady state is zero. Impedances in a circuit can be combined into a single impedance if they are in series or in parallel. Impedances in series can be combined into a single impedance by adding the individual impedances. To understand why, consider the impedances illustrated here and note that because they are in series, the same current goes through all of them. The voltage VAB is the sum of the individual voltages appearing across each impedance. Using the general VI relationship, we can write an expression for VAB and finally obtain an expression for the equivalent impedance, which is the sum of the individual impedances. Now consider the case of parallel impedances. We apply Kirchhoff's current law and represent each individual current as the voltage phasor divided by the individual impedance. Because the voltage across all the impedances is the same, it disappears from both sides of the equation and we obtain an expression for the equivalent impedance. We are now ready for circuit analysis in the frequency domain. Actually, the same circuit analysis techniques as those used for resistive circuits are applicable in the frequency domain. Given a circuit driven by sinusoidal sources, the frequency domain model must be built. This is done by representing inductors and capacitors as their impedances. Furthermore, all sources, currents, and voltages must be represented in phasor form. After that, Kirchhoff's voltage and current law are applied as needed. Moreover, the voltage and current of passive components is related through their impedance. In the first example, a circuit in which a resistor, an inductor, and a capacitor are in series is provided. The series combination is driven by a sinusoidal voltage source. It is requested to find the resulting current. The impedance of each passive element is calculated and the voltage source is represented as a phasor. The impedances are then combined into a single equivalent impedance and the phasor current is obtained using V equals Z times I. The time domain representation can be obtained by applying the inverse phasor transform. In the second example, a similar circuit is provided. It is requested to find the capacitor value that results in a phase angle of -105 degrees for the phasor current. The solution procedure is very similar to that of the first example. The impedances must be combined to obtain the phasor current, which turns out to be parametric because the capacitance value is unknown. After writing the equation for the phase angle of the current phasor and setting it equal to -105 degrees, the value of the capacitor will be obtained. In the circuit given in the third example, 3 impedances are in parallel. One of these impedances is itself the series combination of 2 impedances. It is requested to find the time domain representation of the current in each branch and the voltage across the impedances. If the 3 impedances are replaced by an equivalent impedance, the voltage across the impedances can be obtained by multiplying the phasor representation of the current source by the equivalent impedance. After that, the current in each branch can be obtained by dividing the obtained voltage phasor by the impedance at that branch. In the fourth example, 2 sinusoidal sources are present in the circuit. It is requested to find the time domain representation of the voltage across the 5 ohm resistance. The first step is combining the 3 impedances that are in parallel. After that, applying Kirchhoff's current law at node marked X and using the impedance to write unknown current phasors as voltage phasors divided by corresponding impedances yields the result.